So thanks for the introduction. I'm working at 1&1, one of the largest web hosters in Europe. We have several 10,000 of servers spread to several data centers. And what I want to talk about is replicating whole data centers. That means if you are an experienced sysadmin, you just think that something working on the paper need not really work in practice. And this is one of the themes I want to talk about. So most of you probably know DRBD, which is the state-of-the-art solution for replicating block devices. Why do I replicate block devices? Because replicating whole data centers is only possible with the block device level. If you try it at application level, you are probably lost. Okay, so I'm talking about DRBD plus proxy. There's an additional product which is also suited for long distance replication, and my own product, Mars Lite. Then I'll talk about the differences in the working model of Mars Lite to DRBD, and then the main difference, the behavior at network bottlenecks. And last slide, of course, current status and what's going on. Okay, if you already know DRBD, you know that it's working synchronously, and it's typically constructed as a RAID 1 over network. That means best with a crossover cable, only for short distances, but it's working very reliable there in this application area. And I would recommend to stay at DRBD if you have short distances, in particular crossover cables, because it uses a very low space overhead. It uses a bitmap for storing information during the disconnect state. And this bitmap is the main difference to Mars. If you just compare the last line here, low space overhead, it uses transaction log files. Mars uses transaction log files for recording every write operation, but it records the writes in the exact same order as actually occurring on the device. That's the main difference to DRBD. The bitmap uses less space, but it does not record the order of operations. That's the central difference. Okay, and Mars is working asynchronously by default. The synchronous modes are in preparation, do not yet work, and it's tailored for arbitrary distances. And the outcome of remembering the order of write operations is just that you are consistent at any time, which is not the case with the DRBD. Well, the second use case, you can buy a proprietary edition called Proxy from Linbit, the maker of DRBD, and then you can also replicate over long distances, but the main drawback is buffering in RAM. The buffer is not on a file system or on a stable storage, it's in RAM. And if this RAM buffer gets lost, for example, if you have a network problem, then the buffer is killed. And then you have to resync all this lost data which was in the buffer. And this resync operation is not in order, it's out of order, and it's not an original order of operations. Okay? So you have long inconsistencies during that resync, and the more you lose the buffer, the more amount of data you have to replicate then afterwards, and during the resync phase. So, and that means if you have networking problems, or if you're very slow network, you may end up with a permanently inconsistent mirror there. I'll show an example afterwards. Okay. Just the working model of Mars. It's more similar to databases. You can start with a pre-existing block device which already contains data, and then you will load a kernel module called Mars, and then you get a virtual device, dev Mars my data. You can write data in it or modify the data, and all your modifications, only the write operations are written to a transaction log file in the /Mars file system, which must have the right size for doing that. Okay, then the transaction log files is replicated through a long distance to somewhere else, for example, to the planet Mars or wherever, but it will not really work to Mars, to the planet Mars, because the TCP protocol will not work over this distance. But in principle, the architecture of the software mouse is tailored for the planet Mars. Okay. So this is just applied to your replicated data. And that means the same operations are executed in the same order as originally, but of course it may happen later, 10 minutes later or whatever, in this case. Now we get an example of DRBD problems. In this example, I assume that your network has a problem, and I model it by a throughput limit which is just decreasing. And I'm also assuming that the network, the application load is constant, just for this example. Okay? So what will happen when you start? It's no problem to serve your application throughput through the network at the beginning. It's no problem. But at some moment here, can I use a cursor here? Oh yes. At this point here, you get a problem because DRBD is working synchronously. That means you have to write through all your write operations to the other side, to the secondary side. And if it's not possible, you get high I/O latencies, and after a while, DRBD has to disconnect automatically. Otherwise, your application would get stuck or whatever. So you have an automatic disconnect, and depending on DRBD configuration, it tries to reconnect later. So during reconnect, you have the first problem is that your application load is the same, constant. You cannot serve it, but there's an additional load here because of the resync traffic. All clear. So you have no chance to push it through the network bottleneck here. And what will be the outcome? It's very likely that your mirror is inconsistent at the next disconnect, which surely will happen if it has not been possible to sync all your data, which has been dirtified in the meantime. So this damage is possibly permanently here. Okay? DRBD is not constructed for that case. If you have a crossover cable, it will not happen. Why? Because the crossover cable is no network bottleneck. It either works or not. Okay? And DRBD has also connect and disconnect binary behavior. And this binary behavior is just the right thing for crossover cable. So let's look at the difference to Mars. Mars is recording everything in a transaction log file. And in case the network bottleneck does not allow replication of all your data, then the rest is recorded in the transaction log file. Okay, you can see the actual network throughput is this green line is following the red line here. And the application throughput, the difference, the area here, so the difference is recorded in the transaction log file. So this is the best possible behavior from a theoretical viewpoint. Just uses the network as best as possible. Now finally, let's look at another example. Here we assume that the application throughput remains constant, but the network is flaky. This is a behavior which is observed very often in practice. For example, if you couple two data centers and you have lots of other jobs running backup processes or whatever, then you will notice that the network is not constant. The network is a type of bottleneck which can float around by a factor of 10. We have already observed this at certain times during operations. And what will happen then, if the network is too slow, this area here is the area of the amount of data which is recorded in the transaction log file, and if the network gets better, then it's caught up. Okay? So this is also the best possible behavior you can get from this network. So this is the main idea of Mars. What's the current status? It's GPL on GitHub. The next URL here is not yet ready because the technology domain is one of the new top-level domains, but it should be operational in a month or whatever. Internally at 1&1 we have 15 pilot clusters running for several months, even some older systems from last year or whatever. And we already started a rollout project to more than 250 clusters. We are not yet migrating all our applications, but we are starting with the shared hosting, and other application areas should follow in the next months or years or whatever. It takes a while to migrate everything. So this is our internal status at 1.1, and then other interesting part for you is probably what's going up with the software at GitHub, or is it possible to get it into the kernel? This is my next big task. So I'm planning to come out at the LKML mailing list in the next few months, and I'm currently preparing that. I'm just on the way of splitting Mars into 3 parts. There's a very generic framework doing, it's hopefully usable by kernel developers for other things, not only Mars. Then are some bricks that are internal software components dealing with I/O, but not with block I/O, but asynchronous I/O with arbitrary granularity of requests. That's the main difference. So this is an infrastructure which could be used by kernel developers if they like. And then, of course, there's the Mars Lite application. So I have a 3-layer architecture, the generic part, a first citizen. It's possible to implement other citizens, like stackable file systems or whatever, but it's all in the future. And there's a first application, Mars. And hopefully it's attractive for kernel developers. And if it would succeed, it depends on Linus, but if it would succeed, then you would get it in the standard distribution, which is the aim. Yes, question?
Does it support one-to-n replication, or is it just 2-node like DRBD?
It supports more than 2 nodes. Currently, I have a bug which I've already fixed in a work in a VIP branch, but it's supposed to replicate to arbitrarily many nodes. We have internally some scenarios, but it's not the first priority at the current time. Yes?
On the slave nodes, is there any sort of read-only functionality for the file system?
Read-only?
Yeah, so you can
okay.
have the concept of, I know within DRBD, you can set up the file system so you can still read from the slave if you need to.
Okay.
Yeah. Do you have a similar concept?
Yes. In some way, yes. For example, you can set up a secondary node and just stop not the replication of the log files, but the application. We have time, okay. I switch forward to the appendix. Okay. So I have 3 processes. One is the primary side, and a write request comes in. It's buffered in a temporary memory buffer and first appended to the transaction log file in a sequential manner. Okay, this is crucial for performance. And then it's written back in background to the device in a different order, potentially. This is also crucial for performance. And then you have, this is the first process. The second process is the long distance transfer here. And the third process, which can be switched on independently, is the apply of the log file. So you just stop the apply of the log file, say stop for 1 hour, and then do read-only mounting or whatever. So this is the current solution. And of course, with Mars Full, the planned next release, it's a possible feature to implement snapshots or the like. Also read-only snapshots. If you like it, so we can talk about it. Yes?
How do you define application performance?
Sorry, please, loud.
How do you define application performance?
The application performance. Yes, I have also slides for that. So this is a block replay with a real load. You have also the block replay project, which does some benchmarking of block devices. And this scenario is about 30,000 IOPS on a 50 spindle rate with the very fast disks, the 15K spinning disks. Okay. And parallelism is 7 devices in parallel. And here we are using DRBD on a metro distance line, about 30 or 40 kilometers. So and what you can see here is the latency diagram right out of the writes. The writes are, some of the writes, the maximum here is 70 seconds. So there was one request which took 17 seconds. So you get some hangs due to the network bottleneck. Okay. Now what do you think? The next slide is the same scenario with Mars. Okay. Look at this the scale in the y-axis. This is 1 second here, and this is 10 seconds. The previous slide got up to 100 here. Yes. Not to confuse it. The scale is different in the y-axis. Okay. And of course, the writes are also slower because it has to write all the requests in 2 times. So the theoretical, in theory, the worst case is that it's 2 times slower, but in practice, with practical load, which has a high random I/O rate, then it's even 30% better than a raw device, due to this write-back strategy, but only if you allocate at least 2 gigabytes of RAM for this temporary buffer. So temporary is in this case, not really temporary. But we have some storage servers which have a lot of RAM, so we can do that.
What's your network like that you're using to run the server?
This was a metro network, our own network. We are an AES, autonomous system provider for ourselves. And this is a special line, dedicated line between 2 data centers, but lots of other applications are also running over it.
Start fiber, what bandwidth?
No, it's at least 10 gig. I don't know exactly the details. It's multiple paths and whatever, and I don't know the details. But backups are running over it. A lot of application traffic, of customer traffic, and so on. And you have some load peaks at certain times. And this, the problem is, you always have a network bottleneck. You have thousands of servers, and then you're going to, let's say, 2, 3, or 5 lines or whatever. So you have always the multiplexing problem. You have lots of TCP channels which go physically through a low number of lines. And that's the problem, the principal problem which cannot be solved. If you have a faster line, it doesn't help really. Okay.
What synchronization method were you using in the DRBD? Was that C?
We used all of them, A, B, and C. Okay. It does not help, because if you have a stall, it just stalls at a different point.
Just for the previous.
The previous. Don't know exactly. It's our default, and I think the default is C. I'm not sure. The default should be C. It was a default configuration as from production. Okay, but I can send you the config file if you like. Okay, so lots of questions. Okay.
Are you looking at migrating off TCP to some form of transport that
different transports? Okay.
UDP and allow
Yes.
multicast?
Well, I have a developer branch which already uses multiple TCP connections in parallel. DRBD is stuck to 1 single connection. And here I experimented with 4 parallel connections, and it's really a factor of 4. But of course, it's a heavier load for the line then. And of course, it's stealing network bandwidth from other applications, of course. But you can use traffic shaping with Mars. You cannot do that with DRBD. Try it, and you get the problems of the previous slides. Okay. So I think this is the main outcome. You can have several connections in parallel with TCP. And then traffic shape it. This is what I recommend. If you want to implement other protocols, it's no problem because it's encapsulated somewhere in a very special point, in a single point. So if you want to implement other protocols, no problem from my side. And it's GPL.
About time for just got 1 or 2 minutes, so 1 or 2 more questions.
Yeah?
Have you thought about multicast groups for
Multicast. Okay. 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 Okay, I experimented with multicast many years ago when I was at the University of Stuttgart. My experiences are not good. Okay, is it a valid answer? Okay, so you can implement it, but good luck. As an addition, probably. As an addition. One final.
How does it compare to ZFS replication?
To what replication? CFS, cluster FS. ZFS, no, I never compared it because we are replicating virtual machines or whatever, so it's on a different level. Yes, it's in a block level replication, so it does not directly compare to ZFS or whatever. replications. Of course, you can replicate with cluster FS, for example, which we had done once, but we just switched it off again, and we got back to block level replication for good reasons. I don't want to go into details now. Okay, that was the last question? Okay.